Forget for a moment the usual view. We will not study this black hole from a safe distance, through a telescope, the way we always do. We are going inside. The ship is already falling, and there is no longer any way to stop it. Look up. The entire sky, every star, every galaxy, the whole universe behind us is being squeezed into a single, shrinking circle of light directly overhead. As we fall, that circle grows smaller and brighter, the cosmos folding itself into a bright coin above our heads, while everything around and below us turns to absolute black. Ahead lies the one place in existence that light itself cannot leave. A black hole is not really an object. It is a region, a place where gravity has grown so overwhelming that it tears a hole in the smooth fabric of space and time. Anything that crosses its edge is gone, not hidden, not merely far away, but cut off from the rest of the universe completely, with no path back, not even for light. It helps to know what we are falling into. A black hole forms when a giant star runs out of fuel and collapses under its own weight, crushing a staggering amount of matter into a vanishingly small space. The compression is hard to picture. Squeeze our entire sun into a black hole, and it would shrink to a sphere only about 4 miles across, small enough to sit inside a city, yet still holding every ounce of the sun's mass and pull. Crush the Earth the same way, and the whole planet would vanish into a black marble less than an inch wide. That is the kind of density we are diving into. Gravity concentrated past the point where ordinary matter can survive. For everything outside, a black hole is a wall. We can map its edge, weigh it, watch it bend starlight and shred passing gas. The interior, though, has stayed sealed off from every instrument we have ever built and every equation we trust. The deeper you go, the less our physics is able to say, until at some point it stops speaking altogether. We're not flying entirely blind either. A few years ago, a planet-spanning network of radio telescopes captured the first real image of a black hole, a dark circle ringed by a blaze of superheated gas, the glowing whirlpool of matter spiraling in before dropping past the edge. That bright ring is an accretion disk, gas torn from stars and clouds and heated to millions of degrees while crowding toward the horizon. It is the last light anything gives off before vanishing. We have photographed the doorway. What we have never seen and may never see is what lies on the far side of it. That is the real reason this falling journey matters. A black hole is the one spot in the cosmos where the rules we have spent centuries writing down get pushed until they break. What happens when the physics we know simply stops working? What is actually waiting at the center? This is a descent into the strangest region in the universe, told as honestly as the science allows, from the bright ring fading above us all the way down to whatever lies at the bottom. The first true boundary we reach is the event horizon, and it's nothing like what most people imagine. There is no shimmering barrier, no surface to strike. With a large enough black hole, you could cross the horizon without feeling a single thing. One moment you're outside, the next you're within it, and nothing about that instant would seem special. The horizon is not a wall. It's a line drawn in the mathematics, the exact distance at which the pull grows so strong that escaping would mean moving faster than light, faster than 186,000 miles per second. Since no object can do that, the horizon is simply the point of no return. The size of the hole changes the experience completely. For a small one, no bigger than a city, the punishment starts long before the horizon. For a giant one, the kind that anchors whole galaxies with a horizon millions of miles wide, the curve of gravity at the edge is so gentle that you really could slip across it alive and aware, never noticing the most important boundary you will ever pass. The largest black holes are the ones that let you in quietly, which somehow makes them more unsettling. You could already be inside one and not yet know it. What makes the horizon stranger still is how differently it looks from the two sides. Suppose a friend watches from a safe distance as you fall in. they would never actually see the crossing. As the edge neared, your image would slow, the motion freezing, the light stretching and rendering until you faded from sight, held forever as a dimming smear on the horizon. To them, you never quite arrive. To the one falling, there is no pause at all. You sail straight through and keep going, into a region they can never see. That mismatch sounds like a harmless trick of perspective. It is anything but. It sits at the heart of one of the deepest unsolved problems in physics, the black hole information paradox. Decades ago, Stephen Hawking showed that black holes are not perfectly black. They leak an incredibly faint glow, now called Hawking radiation, and across unimaginable spans of time, they slowly evaporate away to nothing. The trouble is brutal in its simplicity. When one finally disappears, what becomes of everything that fell in? Quantum physics insists that information can never be truly destroyed, yet a black hole seems to erase it without a trace. Nothing about that evaporation is quick. A black hole the mass of the Sun would take far longer to evaporate than the current age of the universe. Not by a little, but by a margin so vast the numbers stop meaning anything. Something like a 1 followed by 67 zeros in years. The giant ones would outlast almost everything else in existence. So the paradox is not an urgent threat. It is a slow, patient contradiction sitting at the foundation of physics, waiting for someone to resolve it. One proposed escape from this paradox is so violent it earned its own name, the firewall. To keep information from being lost, some physicists argued that the horizon of an older black hole might not be calm and empty after all. It might be a seething wall of raw energy. In that picture, the gentle crossing falls apart. The instant you touch the horizon, you would be incinerated, burned to nothing in a sheet of radiation long before reaching the depths. Both pictures cannot be true. Either the horizon is a quiet edge you drift across without noticing, or it is a curtain of fire that destroys you on contact. And right now, nobody can say which. The calm crossing comes straight from Einstein's relativity. The firewall comes from quantum mechanics. Two of our best theories of reality flatly disagree about what would happen to you at the threshold, and the disagreement has resisted every attempt to settle it. The doorway into a black hole turns out to be the doorway into the limits of human knowledge. Whatever the horizon does to you, the fall does not end there, and now gravity itself becomes the enemy. Closer to the center, the pull grows savagely uneven. Your feet, slightly nearer the core than your head, are yanked harder than the rest of you. The difference sounds tiny, but it sharpens without limit as you descend, stretching your body lengthwise while squeezing it from the sides, drawing you out thinner and longer like dough pulled into a strand. Physicists gave this grim process an almost comic name. They call it spaghettification. For a smaller black hole, this strikes early and fast, tearing a falling body apart well before it reaches the true depths. For the supermassive giants, the stretching holds off until you are already far in. Either way, the ending is identical. Long before the center, anything built from atoms is pulled apart. Then, the atoms themselves, drawn into a thin thread of falling matter, every trace of what you were, undone. There is a clean way to feel why escape becomes impossible. Think of space near the hole not as a fixed stage, but as a river, flowing inward, pouring toward the center, and running faster the closer it gets. Light is a swimmer in that river, always moving at the same top speed through the water. Outside the horizon, the swimmer can still gain ground upstream. At the horizon, the river rushes inward exactly as fast as the swimmer can go, so light hangs in place, sprinting and getting nowhere. Past that line, the current wins outright. Space itself is falling faster than light can climb, and nothing moving through it, not even light, can ever turn back. Time behaves just as strangely as your body. Gravity does not only bend space, it slows time, and near the hole, that effect turns extreme. The deeper you fall, the faster the outside universe appears to run. There is a haunting idea that as you plunge in, you might look up and watch the entire future of the cosmos play out overhead in fast forward. Stars igniting and dying, galaxies wheeling, the universe aging to its very end in the time it takes you to drop. The truth is subtler. Someone plunging straight through actually crosses too quickly to watch eternity unfold. But for anyone able to hover just outside, clinging to the edge, the outside universe really would race ahead, days and years and ages ticking past in moments. Time near the hole is not fixed, it bends to where you stand. The view itself would be unrecognizable. The black hole's gravity bends the paths of light so severely that the sky no longer sits where it should. Stars that are truly behind the black hole have their light curved around its edge, over the top and around the sides. So the darkness ahead appears wrapped in a warped halo of the universe behind it. Up becomes a distorted ring. Down is a growing pit of nothing. Every familiar sense of direction quietly comes apart. And then there is the darkness. As the fall goes deeper, the bright ring of the outside universe above shrinks and shifts. The light reaching down has to fight an ever stronger pull, bleeding away energy as it comes, sliding from white to red and last to nothing. One by one, the stars wink out. The bright coin overhead narrows to a point, flickers, and is gone. For the first time, you sit in a place with no light at all, not because none is nearby, but because light can no longer reach you from anywhere. Total, final, absolute dark. It's worth stopping here in the dark to admit how far past solid ground we have come. Everything up to this point still rests on physics we can test. From here down, we enter territory where our finest theories openly break, and where the honest answer to most questions is that nobody knows. What waits below is stranger than the fall, and the ideas people have offered to explain it are stranger still. Keep going, because the bottom of one of these may say something about where everything came from. At the center, according to Einstein's own equations, sits the singularity, and it is less a place than a catastrophe. All the matter that ever fell in, an entire collapsed star or far more, is crushed into a single point of zero size and endless density. Gravity there climbs toward infinity. The curve of space and time grows infinitely sharp. When a physical theory starts handing back infinity as an answer, it's not revealing a true feature of nature. It's confessing that it has failed. The singularity is the exact spot where general relativity, the most successful description of gravity ever written, throws up its hands and quits. This was not a fringe idea or a quirk of one tidy solution. In the 1960s, the physicist Roger Penrose proved that once a region collapses past its horizon, general relativity makes a singularity essentially unavoidable. Not a rare special case, but a near certainty baked into the theory. The work was so fundamental that it earned a Nobel Prize decades later. Relativity does not merely permit the singularity. It demands one, and in the same breath admits it cannot describe what that singularity is. Stranger still is what those same equations say about the journey there. Outside the hole, you move freely through space while time carries you helplessly from past to future. You can turn left or right, but you cannot stop tomorrow from coming. Inside the horizon, those roles swap. Space and time trade places. The center stops being a location ahead of you in space and becomes a moment ahead of you in time. Falling toward the singularity turns into something as unavoidable as next week. You can no more steer away from it than you can steer away from your own future, because every path you might take now leads to the center. The center is no longer a where, it is a when. This is the part that breaks intuition hardest. Once you are past the edge, no engine is powerful enough and no maneuver clever enough to avoid the singularity, for the same reason you cannot dodge the next second of your life. The collapse is not a hazard you might outrun with enough thrust. It is woven into the structure of time itself within that region. Whatever the true center holds, Arriving there is the one certainty left. And yet almost no physicist believes the singularity is genuinely real, an actual point of infinite density. Most read it as a placeholder, a flashing warning light that our theory has run out of road. To learn what truly sits down there, we would need a working theory of quantum gravity, a way to fuse Einstein's gravity with the quantum rules that govern the smallest scales. No one has built one yet. So, at the deepest point of the fall, science hands us not an answer, but a question, along with a handful of daring guesses about how to replace it. The first guess removes the singularity completely. It comes from string theory, which proposes that the smallest pieces of reality are not points but tiny vibrating strands of energy. Apply that same idea here and the picture shifts drastically. Instead of empty space wrapped around a deadly point, the whole interior fills with a dense, churning tangle of these strings, packed all the way out to where the horizon would be. This is the fuzzball. In this view, there is no bottomless pit and no singularity at all, just an exotic ball of strung-out matter with a genuine surface, closer to a strange star than a hole. A fuzzball would glow with exactly the faint radiation Hawking predicted, which is part of why the idea is taken seriously. If it holds, the hole has no interior in the way we pictured. You would simply meet the surface of the fuzzball, and the riddle of the lost information quietly dissolves. A second idea keeps the strangeness but aims at somewhere extraordinary. Buried in Einstein's own mathematics is a structure often called an Einstein-Rosen bridge, better known as a wormhole. In its simplest form, the geometry of such a hole can be extended on paper into a tunnel, a throat in space and time that links to another region of our universe, or even to a different universe entirely. For a long time, this was dismissed as a mathematical curiosity, since such a tunnel would pinch shut almost instantly and crush anything trying to pass. Yet, the notion refuses to die. It hints that the bottom of such a hole might not be a dead end at all, but a passage, a door whose far side opens somewhere we cannot picture. Such a tunnel, if it existed, would need a strange exit. Einstein's equations contain a mirror image of the black hole called a white hole, a region nothing can enter and that instead pours matter and light outward, a black hole running in reverse. On paper, the far mouth of a wormhole can look exactly that. No one has ever found a white hole, and they may be purely mathematical, yet it plants a striking thought that the violent inrush of a black hole in one place could be matched by an outrush somewhere else, even by the sudden outward flood of a whole new universe. The third proposal is the boldest, and it turns a black hole into a cradle. The physicist Lee Smolin proposed that when matter collapses toward the center, quantum effects might halt the crush just short of a true singularity and make it rebound, bouncing outward into a brand new region of space and time. From within the parent hole, no signal appears to leave, but on the far side of that bounce, a fresh universe blossoms into being complete with its own Big Bang. In this picture, the violent end of time at a singularity is the very same event as the beginning of time in a new cosmos. Smolin carried it one step further. Each baby universe, he suggested, would be born with slightly different physical laws, and the universes best at producing black holes would leave the most offspring. Over countless generations, a kind of cosmic natural selection would favor universes finely tuned to make black holes. If he is right, then every black hole in our sky is a seed, and our own universe may itself have been born inside the black hole of some older cosmos. None of these can be tested today, and they may all prove wrong. What ties them together is a shared refusal to accept infinity as a real answer. Each one tries in its own way to imagine what nature actually does where our current physics surrenders, and each replaces the dead point at the center with something that continues, a surface, a tunnel, or a doorway into a new beginning. All of this circles back to a question that sounds like science fiction, but follows from serious physics. Could we already be inside one? not falling toward a black hole, but living within it right now. The thread that leads there is called the holographic principle, and it grew straight out of studying black holes. Physicists noticed something odd. The maximum amount of information a black hole can hold depends not on its volume, but on the area of its horizon, its surface. It is as if everything that ever fell inside is somehow recorded on the two-dimensional boundary, like a vast cosmic hard drive written across a sphere. Taken to its limit, the principle suggests something dizzying. The three-dimensional reality we move through, with all its depth and solidity, could be the projection of information encoded on a distant, lower-dimensional surface. The world might be a kind of hologram, and we would never feel the difference from within it. Push that thought outward to the whole cosmos, and it arrives at a strange door. Some physicists have seriously asked whether our entire universe sits inside a black hole belonging to a larger one, and whether the boundary we call the edge of the observable universe behaves in certain ways, like a horizon seen from the inside. The expansion we measure, the matter we are made of, even time as we live it, would then be the interior of something far greater, viewed from within. It remains speculation, but it is the kind of speculation that grows directly out of taking black holes seriously. It is worth being honest about how speculative the far edge of this gets. We have photographed a black hole's shadow and tracked stars whipping around invisible giants, but every claim about the interior rests on theory alone, untouched by any direct measurement. The holographic principle and its cousins are mathematically serious rather than idle dreams. Yet for now, they live in the gap between what the equations permit and what we could ever check from inside. Which returns us, at last, to why any of this matters. We will almost certainly never send a probe into a black hole and get an answer back. The whole point of a horizon is that nothing returns, and we still keep falling toward these objects in our minds, building theory after theory, precisely because the interior of these objects is where the story of everything seems to be hiding. Science keeps probing the place where physics ends, because that may also be the place where physics, and perhaps we ourselves, began. To ask what is inside a black hole is in the end to ask where we came from. The ship has long since gone silent. The bright coin overhead vanished ages ago. Whatever the center truly is, a wall of fire, a tangle of strings, a tunnel, or the very first instant of a universe waiting to be born, it has kept its secret, the way it has kept every secret that ever crossed its edge. The deepest place in the cosmos is still dark to us. We keep falling toward it anyway. That last idea that everything we know might sit inside a black hole has only grown stronger as new measurements arrive. We explored the most striking version of it in our video on the new study suggesting the universe might be a rotating black hole. It is the natural next step from the bottom of this one. Stay insanely curious.